In this presentation, I want to provide a Haskell-oriented overview of the topics in the software languages book. I call this the Haskell Road to Software Language Engineering and Metaprogramming. So here is a table of contents for the book. I mean, there's a part 1, it's an introduction. Part 2 develops the foundations and implementation aspects of abstract and concrete syntax, and it dives into basics of metaprogramming. In part 3, it's more about programming language theory, so there's operational and denotational semantics, as well as type systems, and also some coverage of the lambda calculus. And part 4 sort of gets deeper into metaprogramming by showing some more advanced metaprogramming techniques. So we are going to briefly talk about the following topics here. So this is obviously quite a rich coverage. I mean, there's interpretation, compilation, term rewriting, attribute grammars, transformation, and so on and so forth. So all the code is available online. Before I continue and talk about all these different topics, I should make clear that this presentation here is just meant as a Haskell-oriented overview of the topics. It's by no means meant to really explain all the underlying concepts. All right. So let's start with the first topic, object program representation, which is obviously fundamental to metaprogramming or fundamental to software language engineering, that we somehow can represent software artifacts in metaprograms. It's pretty simple. So I'm just going to show like the basic Typeful representation approach and also a universal representation approach. So here I'm going to use a very simple expression language. It's going to show up time and again. So we have expression forms like true, false, 0, if, and so on and so forth. So this is the Typeful representation approach in Haskell when we use algebraic data types. For some reasons, for example, when we need to perform certain kinds of generic operations or when we need to perform serialization, we might also need a universal representation. So in a very simple case, we've got a data type term wrap. So the constructor is encoded as a string, and then the children terms, the subterms, are also just encoded as a term wrap. Okay, so now slightly more interesting, let's talk about the topic of parsing. I mean, quite obviously, again, it's important for software language engineering that we can parse text into trees, or in the context of model-driven engineering, this would be called text-to-model. So the following aspects should be emphasized here. Just the basic parsing algorithms. Well, I will show one. Then implementation of parsers based on recursive descent, and then implementation of parsers by using parser combinators. So here's a very simple baseline encoding of top-down acceptance. Up here you see some possible encoding, let's say representation of grammars being lists of rules, rules being labeled, left-hand side non-terminal, right-hand side sequence of grammar symbols being either terminal or non-terminal. So this is top-down acceptance, so it uses a kind of a parser stack here, and we start by looking up the start symbol, which we assume is the left-hand side non-terminal of the first rule. And then here are here's the consumption step of top-down acceptance, that the terminal is also found in the input. And here's the expansion step, that the non-terminal is replaced by some right-hand side. So the right-hand sides for the non-terminal at hand are looked up by the list comprehension. And then in fact, we consider all possible right-hand sides. So this is a very naive algorithm. I mean, it may not even terminate necessarily, for example, when we have left recursion, but it's sufficient to discuss these issues like impact of backtracking or limiting backtracking, possibilities for non-termination. So it's good for discussing basics of parsing. All right, so this is how we could implement a parser by recursive descent. So in the comments here, I show the grammar rules. So this is about basically a language of binary numbers. And so we implement the grammar rules just directly by functions that take a string and maybe return a remaining string. And here at the top, we assume that we consume the entire input. Well, and then we just implement each non-terminal by a function, and we use the bind combinator for sequential composition, and we have a match function to consume terminals. So this is just common recursive descent style. Here we have an acceptor for a simple domain-specific modeling language. So this is about like finite state machines and this sort of textual notation here, initial state, two other states, bunch of transitions. And these functions here use parser combinators such as sequential composition or many, which is like the EBNF star, or optional, which is like the EBNF question mark, and so on. So we use these parser combinators to assemble an acceptor for finite state machines. Next topic, interpretation. Quite obviously, this is at the heart of software language engineering, because interpretation is one major style of language implementation, and also it gives rise to the notion of definitional interpreters. That is, we use one language that we understand very well to implement another language so that we understand this object language also very well. And so I'm going to go through a few aspects here: recursive evaluation as a baseline, and then execution while also using stores as needed for imperative languages, and then also evaluation when using environments but for bindings, and then also the issue of stepwise execution as opposed to just recursive evaluation. Okay, so here's a very simple interpreter for the expression language that we saw earlier. So we just really descend into all the terms in all the expression forms, and we have recursive applications of evaluate all over the place to recursively turn this kind of expression forms into either an int or a bool. Here is an interpreter for a simple imperative programming language. So we have an empty statement, assignment, sequential composition, if statement, while loop, and some expression forms. And when we look at the function signature for the interpreter function here, we see that we essentially map statements to store transformers. So we operate on the store, in particular when we have an assignment here. The right-hand side expression's value is assigned to the left-hand side's variable by an appropriate insertion or modification of the incoming store M. Here we have the interpreter of a simple functional programming language, and we need environments here because we might want to bind actual argument values to formal argument names while evaluating the body of an applied function. So what we do here is, yes, we look up the function, we evaluate the actual argument expressions, we zip together the formal argument names and the actual argument values, and we use this data structure as the new environment within the scope of evaluating the body of the function. Here is an interpreter for the finite state machine language. So again, here we see how we represent finite state machines. So we've got a data type for FSMs, and FSM is just a list of states. A state consists of a Boolean saying whether the state is initial or not. A state has a name, of course, and otherwise it has a list of transitions that all depart from that given state. The transition term is an event and maybe an action and a target state. So I'm not going to explain this interpreter in detail, but it should be clear that we have stepwise execution here because the incoming input, which is a sequence of events, is processed by an fold L. So we use step-by-step, transition execution over the input sequence here. Okay. Next topic, software analysis. Again, this is also very important in software language engineering and metaprogramming. We might want to implement a type system of a programming language or a domain-specific language. More generally, we might have some static semantics of a domain-specific language or a modeling language. Other forms of software analysis are needed when we do software reverse engineering or program comprehension. So we are going to discuss some basic aspects here, namely type checking just based on Boolean constraints. We could also discuss type checking when we try to synthesize useful error messages. I skipped this here. And then some languages may not even have an interesting type system, but nevertheless we might need to check some sort of well-formedness. We also give an example of that. And as a very simple example of reverse engineering, let's do some fact extraction for software magic. All right, so here's a type checker for the simple expression language that we have seen earlier. Again, we just go over all the expression forms and we check that the operands are of the right types. I mean, natural numbers versus Booleans, and we return the appropriate result type. And of course, type checking may fail, and therefore we have a maybe type here in the result of the type of function. So these are what I call Boolean constraints-based type checking implementations. All right, so now let's consider again finite state machines. We don't have a real type system here, but there's all kinds of interesting constraints a well-formed finite state machine should meet. So here we have a list of constraints. So all the state IDs of the distinct state declarations should also be distinct. There should be exactly one state that is marked initial. All the target states and all the transitions should be resolvable. They should point, that is, to a state that is declared. All the transitions for a given state must be deterministic. That is, there cannot be like two transitions with the same source state and the same event. And all the states should be reachable from the initial state, because otherwise it would indicate some form of dead code. And here's how we implement all these constraints by some form of list comprehension, some form of analysis, traversal over the object representation at hand. Here is a very simple fact extraction to determine a software matrix. Let's say we look at imperative programs, and let's say we want to know how operators are used within the imperative programs. Okay, let's assume we have a program for Euclidean division here, and this analyzer is supposed to tell us that within the program addition is used once, greater equal also once, and subtraction once as well. So the analysis in this case is programmed essentially by a generic traversal over the object program representation, such that when we reach expressions, especially unary and binary expressions, then we intercept these expression forms and we turn the operator of these expressions into an appropriate string. So here we use scrap your boilerplate style generic programming. Next topic, software transformation. Again, a very central topic in software language engineering. You need it also just for pretty much any serious language implementation, and by itself you also need it in software re-engineering. So I'm going to show two aspects here. One form of refactoring, well, and that's actually it. I'm not going to show program optimization here, but this would be another obvious candidate for discussing software transformation. Okay, so we're going to do renaming for finite state machines. This is kind of illustrated here. So we want to rename state ID locked to closed and state ID unlocked to open. All right, and this is how we do it. So I'm assuming here, and you see this here, that the transformation first should establish that the precondition is satisfied. Well, then it should compute the result from the incoming software artifact. And then we might want to check the post condition. We might also leave out checking post conditions if we are sure enough that it is implied. Okay, so in this case, the precondition is about the fact that if we rename I to I prime, that I should actually be present in the incoming FSM, because otherwise there would be no point in renaming. And also that I prime, that is the target of renaming, should not be present in the incoming FSM, because otherwise you would create a crash. And other than that, the actual transformation, the actual renaming is some sort of traversal over the FSM-like representation let's skip it here. Another topic I want to cover, software composition. It's relevant in the context of modularity for software languages. So I'm going to demonstrate it by means of model composition, that is sort of merging models. More specifically, we are going to merge models for finite state machines. So this is like illustrated here. So we have like a simple baseline FSM about the transitions between locked and unlocked state, and here we have some extra part of the finite state machine that is dealing with exceptional behavior, and we just want to have a composition operator, merge or plus, that gives us the combined FSM. Just as an indication, here is that operation, and we also assume again that we have de facto some sort of constraint on the incoming and on the resulting finite state machine, very similar to pre and post conditions. And the actual merge operation is actually implemented by means of appropriate addition operators at the level of state declarations, at the level of transitions, and so on. All right, compilation. I mean, just like interpretation, compilation is a major mode of language implementation. The software language book doesn't go really much into detail here because there's great material out there on compilation, but it at least tries to cover compilation at some basic level. So I'm going to show you a simple assembly language and a simple machine language, and also hint at some code generation. Okay. So here is an illustration of an assembly language. It's stack-based. It uses jumps. It uses it has symbols for memory address. It has labels, symbolic labels for jump addresses. And so this is some representation of Euclidean division where we want to divide 14 by 4. Okay. This is the same program, but now the level of machine language. So all the symbolic stuff is gone. So there are no symbolic jump labels anymore, but it's more like instruction counter based, and also access to memory addresses, uses directly addresses and no symbols for that. All right, and so here we have the first part of the compiler, which translates statements into instructions of the assembly language, and it's a straightforward recursive process, and you see how we concatenate together all the various instruction sequences. All right, formatting, another topic. I mean, it's sort of the opposite of, if you like, of parsing, and we need it when we need to generate source code, and in the context of model-driven engineering, it would be called model-to-text. So let's say we want to pretty print finite state machines. So finite state machines should be laid out like this, that we use appropriate indentation, that we use appropriate vertical layout, and that some of the things are, like the transitions, are horizontally laid out. And so here's how we write a function from FSM to doc, which is basically an abstraction over text, and we use various pretty printing combinators for horizontal composition, for vertical composition, for indentation to achieve this effect. All right. So here is a template processing based approach. It is also supposed to effectively pretty print a finite state machine. So we see this here, an FSM comes in and a string comes out. So up here we define some templates. From the template down here we look up the main template. We set the attribute of the template processor, that is we sort of pass in the FSM, and then we invoke the rendering process of the template processing engine. So the templates use parameters and the loops in a sense, and also conditions to produce the right output. Okay, term rewriting. Term rewriting is a more fundamental, a more systematic approach to writing, especially program transformations, rather than just writing ad hoc functions or maybe visitors in an OR language. So we are going to cover some aspects here, like the basic notion of rewrite rule, then the notion of rewrite system, which includes basically some notion of normalization, and then what we call strategic programming. This is when you provide more flexibility in terms of how rewrite rules can be applied. As the motivating scenario here, we use again some expression language, and we start from these laws here for the expression language. Some of these laws, like the first few ones, they are quite obviously what you might call simplification rules. Well, then you have commutativity here. These are not quite simplification rules, but you might need them in order to find more opportunities for simplification. And then we have associativity here and distributivity. So these would be rules maybe that you use for normalization, if you like, of your expressions. Okay, so we can basically take the simplification rules for units and zeros of addition or multiplication, and we can turn them directly into a function from expert to maybe expert, because these rewrite rules in a sense can apply or not. So we always have to have a catch-all case, which goes to nothing. And down here we see how simplification succeeds or fails for different reasons for given expressions. So application might fail because, well, there's really no regex, or application might fail because maybe the regex is somewhere deep in some subterm and this function as it stands doesn't really drill into subterms. Or simplification might also fail because we would need to take into account commutativity. And that's what we do here. So we actually also encode commutativity by another function, commute, which also goes from expert to maybe expert. And then here we just try out simplify in two ways, namely once as is and once by preprocessing the term with commute, which means we can now perform more simplifications. Anyway, so generally in term rewriting, what people do is they assume or they provide some sort of normalization strategy. Classically, it's very popular to use repeated once bottom up, which is essentially innermost. But in modern rewriting, people use different kinds of strategies, such as full top down, or one stop down, or stop top down. And all these normalization strategies are essentially programmable just by means of recursion and some other straightforward combinators, once you are able to access immediate subterms in this manner here. But let's not get too much into detail. So basically we can develop a full library of traversal strategies in Haskell, and by this we can pick normalization strategies, and by this we can actually apply, simplify in many different ways, and we can perform normalization as we see fit. Okay, quasi-quotation. This topic is important when we come to language embedding, for example. I mean, when we want to embed one language into another language. For example, we might want to embed SQL into Java. So I'm going to discuss two aspects here. One is just parser embedding as such, that we can parse one language from another language. And then we also get to metavariables or splices, which results in a stronger integration, amalgamation of host language and embedded language. So here we see how we could use the syntax of finite state machines directly in Haskell. So what we need to do is we need to use the quasi-quote brackets, and we need to say what language we want to switch to. And the language obviously is called FSML. And then within these brackets, we can place the finite state machines. Underneath, this syntax is converted into some abstract syntax of finite state machines. And in fact, it's also further translated into Haskell expressions. So this is, by the way, the quasi-quota that we need in this case. We need to tell Haskell how it should deal with FSML syntax when it appears in an expression rather than a pattern or a type position. And what we essentially do is we just use a normal parser for FSM. And by this we get an abstract syntax tree for FSMs, and then we use some generic conversion here which translates the FSM ast into a Haskell ast. Okay. And here's an indication for a more sophisticated quasi-quotation use case. So let's say we want to program rewrite rules on our expression language by using concrete syntax of the expression language. So as a starting point, imagine that we have again these simplification rules. Well, we know how we can implement them just in plain Haskell like this. So that is, we use patterns using algebraic data type constructors. And now by having a quasi-quota for the expression language within Haskell, we can now use both on the pattern positions of our equations, but also on the right-hand sides, we can use the concrete syntax of the expression language, and we can even talk about metavariables, that is Haskell variables that bind to certain sub-expressions and that we bind on the left-hand side in the patterns and then can use again on the right-hand side. Attribute grammars. This is a classic topic in language implementation, and attribute grammars are specifically helpful in analyzing programs and in modeling translation. So I'm going to cover these aspects here: attributed concrete syntax trees, and attribute dependencies as they are modeled by attribute grammars, and I'm going to show how lazy function programming is sufficient in implementing attribute grammars. So here's a simple attributed tree where we imagine to compute the decimal value of some binary number. So this is 101.01, and it should get the decimal value 5.25. And what we see here is that all the various nodes in the tree have value attributes. That is the value contributed by the corresponding subtree to the final result. Okay, so here is an attribute grammar for the underlying binary to decimal number conversion. I'm not going to go into detail, but it works by having value attributes. It also works by having position attributes for the bits in the bit sequences, and we also deal with the lengths of bit sequences. Sort of interesting aspect here is that we seem to synthesize the length of the bit sequence, and then we pass it back down as an inherited attribute for the position of the heading bit of a bit sequence. And so when we implement this attribute grammar in a functional program, this is how we do it, this sort of interesting dependency also shows up here. So basically each non-terminal corresponds to a function here, and there's one equation per production, and this is how we actually implement the top level production. And so you see we compute the length and the value, and the position is computed from the length, and then we pass it in back into here as an argument. So obviously for this to work, we rely on lazy function programming, showing like sort of the computational or the declarative status of attribute grammars and also the expressiveness of function programming. Okay, multi-stage programming. It's very relevant for generative programming. That is when we want to write programs that generate programs, maybe in order to account for abstraction mechanisms used in programming, and the generation should kind of eliminate the performance overhead caused by use of abstractions. So the use case here is inlining. So we want to inline to get maybe just rid of overhead of recursion, and we are going to use Haskell's quasi-quotes as provided by template Haskell, and we also show how this can be less and more typeful. Okay, so this is our simple use case. So we have a power function, and so we imagine that if we would be able to fix the exponent of the power function, then we want to get code at compile time which does not involve recursion anymore, but rather is specialized in a way that it looks like this. And this is what template Haskell is obviously good for. This is how we would write it in template Haskell. So rather than taking two ints and returning an int, it now takes the int for the n, and it takes another argument and returns essentially code. Okay, this is how we see it returns code. And then here we use splicing to generate the code so that we really specialize it for n. Okay, and just as an idea here, more recently template Haskell has also been extended to allow a more typeful approach. So here we see that we do not return any sort of expression, but actually an expression that should compute an int. And we use the typeful brackets here. Okay. Formal semantics. The assumption is that one cannot be able to do really rigorous software language engineering, language implementation without having some understanding of semantics. So we're going to briefly discuss big step, small step, operational semantics, as well as denotation semantics. All right, so here we have a few big step rules for the simple expression language. And here we map them to equations of an evaluate function in a one-to-one manner. So this is actually cool that we can do it in a one-to-one manner, which is maybe not so obvious, because look here that we have two rules dealing with the pred construct, and so we also have two equations dealing with the pred construct here. So we use pattern guards in some nice way to make sure we have a very systematic and modular mapping. The same can be done for small step. Let's go on. And here's how we deal with denotational, compositional semantics. So this meta notation can just be turned into very simple recursive mapping, and some sort of, let's say, informal or semi-formal definition of the combinators used by denotation semantics can be easily implemented in Haskell. For example, here for the semantic combinator for the while statement, we use a fixed point combinator. Abstract interpretation. It's a powerful technique for program analysis, and it's semantics based, of course. And I'm going to briefly discuss the notion of abstract domains as well as semantic algebras. All right, so when you do program analysis with abstract interpretation, then you typically figure out the domains involved in the analysis. For example, when you want to do sign detection, then you go from the concrete domain of numbers to the abstract domain of signs. And here we see how we can actually model the domain of signs as an instance of the num-type class. And for example, the type class member from integer is what you would call abstraction in the context of abstract interpretation, that is going from a concrete number to an abstract value that is a sign. So semantic algebras, that's basically the building block in order to be able to switch between different semantics. So here we see essentially a signature for semantic algebras, and this signature can be implemented in different ways. We can implement it to get exactly our default semantics. We can implement it to get a type checker that adheres to the compositional scheme. We can implement it for a program analysis that performs sign detection, and in many other ways. Partial evaluation, the final topic here. It's a technique for program optimization. It's essentially semantics based. I'm going to just very briefly show how it helps in specializing programs. Here's the equation for specializing function applications. So it involves some issues like evaluating the, partially evaluating the arguments of the function application, dividing arguments into static and dynamic arguments, some sort of memorization of the current applications, also in terms of the static arguments, and essentially possibly returning a specialized form of the application. It's pretty complicated. Okay, but that's it. So let me wrap up. So please get in touch if you want to use this material, or if you some way want to contribute or want to provide feedback. I'm also interested in other people's experience with this sort of software language engineer, metaprogramming topic space. Thank you.